coming. So I'm very happy that László is here today to join us. László Kozma did his PhD in Saarbrücken with Raimund Seidel, and then spent some time in Tel Aviv and Eindhoven before, well, settling in Berlin for a while now. He's worked on a broad range of things, many data structure things, as you can see on the slide. I always learn something new when he's presenting things. And I also invite you to check out his website, because at least at some point he found the time to have lots of side hobbies and projects, which are very inspiring. It's always fun to spend some time on those on this page. But without further ado, let's welcome László, and looking forward to your talk.
Wow, thanks, Sebastian. Can you hear me? Is this on? Is it too loud, or it's okay? Thanks, Sebastian and Cecile, very much for the invitation and for putting together such a nice conference. I'm very happy to be here. So what I will talk about is maybe a little bit exotic to this community, but I hope it's not too alien. So it's about analysis of algorithms. So I should say, so it's using extremal combinatorics. So I should say a few words about extremal combinatorics. So typically, in extremal combinatorics, you study questions like how large an object can be, or how dense it can be, or how many of them can there be if this object X avoids some object Y. So if you put some constraint on some object, what can you say about it? And a very typical question is, how many edges can a graph of n vertices have if the graph doesn't have a clique of size k? Okay, this is actually one of the first questions of extremal combinatorics, and it was solved by Turan in 1941. This is the answer. It's quite precise. There are even extremal examples. It's a k-1 partite graph achieves this bound. And so this was maybe the first. Some special cases were studied before, but this was maybe, it's not just a typical question, but maybe the first question of extremal combinatorics. And afterwards, of course, many other subgraphs were studied, and it's still actively researched. Some cases are still not fully understood. Here is a picture of Turan, so one of the founders of extremal combinatorics. And so I will mention some results like this, but I mostly won't talk of graphs, but about matrices, which is very similar. So I could ask, so I should say you can think of it as 0, 1 matrices, but for some reason, we often mark just zeros with empty spaces and ones with the dots. So I will show these matrices with a lot of dots, but you can really think of them as 0, 1 matrices. So we can ask questions like this: how many dots can an n by n matrix have if it avoids some pattern? And what do I mean by that? So here is one pattern, for example, this 2 by 2 matrix. And this is actually contained in this matrix because I have 4 dots which have this configuration. So the exact definition is that I have a submatrix of the same size as the pattern, which matches the dots. It doesn't have to be a contiguous submatrix. So the pattern could also have empty places, and those are don't cares. So those I don't have to match. So for example, this pattern also occurs in the matrix because I have these 3 red dots in the same configuration. Yes?
Yeah, I just want to check. You want them to be in the same order?
Yes. So the order is sensitive. Yes, of course, for the first one, it doesn't matter, but here it really matters that you want the first one to be above the other 2, and so on. Yes. Exactly. Yes. So it's kind of an ordered version of the graph.
So
yes?
strictly a matrix issue, not a graph issue. We haven't got any issues of permutations of rows and columns to make the graph slightly more.
No. It's really in this order. And just to give an example, this pattern, for example, is avoided in this matrix because you don't have 4 dots which would have this configuration, that 2 are on the same row, and they are somehow shifted in this way. Okay, and you can ask the similar question. We can define this extremal function of a pattern, which means how many dots can you still have while avoiding that pattern? Okay, and it's clearly between 0 and n squared. So we could ask, for example, okay, the first one, can someone guess what is the extremal function? Or does someone know? And so as it was mentioned, this is actually a graph, okay? So this is the same as saying a bipartite graph, which avoids a 2x2, 4 cycle, basically. So it's a, what do you think? Is it like more than n to 1/2 or less? N to 3/2, yes, very good. So it's not a trick question. It's exactly n to the 3/2, yes. So I said 1.5. I meant 3/2, yes. So this is the famous Zarankiewicz problem. It's exactly the bipartite graph avoiding C4. Okay. So the second one, you may think a bit: is this a stronger restriction or it's milder? Should it be more or less? Well, it turns out to be linear for this one. Okay, so if you have a superlinear number of dots, you will have such a pattern. And this one happens to be this strange n times alpha n, this inverse Ackermann function. It's related to this Davenport-Schinzel sequences. Okay, so here is a very broad class. I could consider all the patterns which are a permutation matrices. So every row and every column contains only one. And it was conjectured that for all these patterns, the density is linear. Of course, with a constant depending on the permutation. So if the permutation is fixed size, then it should be linear. And actually, this was proven in 2004. So it's a very surprising result that even if you have a 100 by 100 permutation that is avoided, you cannot be superlinear density. Okay. So there are many other results. So this function can take many possible values. There is a large body of work on this question. Okay, so what I would be interested in is to somehow use this to analyze algorithms and to model structure in the input of algorithmic problems. So let's start with the first. And I will do I would say, nice example, which is due to Seth Petty, who pioneered this type of analysis. So it's somehow to showcase how you can analyze an algorithm with this technique. So the algorithm or data structure we look at is the union find data structure. We want to maintain a collection of disjoint sets, and we want to be able to merge two sets, or given an element, a pointer to that element, say in which set it is. Okay, so the typical solution is we maintain these sets as trees. And then if you want to locate an element X, you walk up to the root, and that tells you in which set your element is. Okay, and you want to implement this union where you have to merge then two trees. And we do the simplest possible thing. We link one of the trees as a child of the root of the other. So in Bob Sedgwick's book, I saw this is called the quick union. So you don't do anything smarter, you just arbitrarily link the two. Okay, and finding X, you just walk up from X to the root, but you also don't want this path to remain long, so you also compress the path. So if you walk up from X to the root, then all the nodes which you meet on this path, you link directly under the root. Okay, so you kind of flatten the tree while you do this, so that the finds become cheaper afterwards. Okay, and the question is, what is the cost of this? If you have a long sequence of operations, what is the amortized cost, or what is the total cost of all these operations? Okay, and there was a classical analysis of this, but here is a simple analysis. So first, we view all these trees as if they were a single tree. So somehow, for the sake of analysis, we do all the unions up front. We merge all these trees into one. And now these path compressions don't necessarily go up to the root, right? They go only as far as they would go in their trees. So we have this general path compression where we can compress the path from some X to Y. Okay, and we want to say what is the cost of n such path compressions. Okay, and the cost is how many nodes we touch on these paths. Okay, is the setup clear? It's a classical algorithmic or data structure question, and we want to analyze this sequence of operations. And here is a nice way to do it. We encode the entire execution as a matrix M. How does that look? So on the rows, we put the time, so the different operations, and on the columns, I put the nodes of this tree in some order in the post order of this tree. And then at an entry of the matrix xj, I put a dot exactly if that node x was touched during the jth path compression. Okay, so I'm kind of for every node which is touched, I put a dot in this matrix. Okay, and then the total cost is just the density of this matrix. The total cost will be how many dots I have in this matrix. So this matrix somehow captures the entire execution of the algorithm or data structures, and I want to say what is the total number of dots. And I have a simple observation that this matrix cannot contain this pattern. Okay, it's a one paragraph proof or why it cannot contain this pattern. So suppose this matrix contains this pattern. So what does it mean? At time I, so at the ith compression, we touched x and z. At time j, we touched x and y. So it means that x has to be at some point on the same path with z, and then at some point the same path with y. So x could be the ancestor of both y and z, but then this would not be the correct post-order sequence. So really the only case that can happen is this, that x, y, and z appear in this sequence on a path. Right, so this x, y, z is this post-order sequence, and x, y, and z appear on the path like this. And then at time I, we compress x and z. So x and z are compressed. But if x and z are compressed, then also y has to be compressed because we are compressing paths. So then after the compression, x and y become siblings. So then at a later time, they cannot be compressed together because they are siblings. They are not on the same path, and they will never be on the same path again. Okay, so this is impossible. This pattern cannot occur. And then we go to the library and check out what's the extremal function of this pattern. And so Gabor Tardos did the hard work for us and showed that it's n log n. So we get for free the analysis that the cost of this execution is n log n. Sorry? Is bounded by, upper bounded by n log n, but it turns out that this is tight even the constant. So this is I mean, it's a simple, this gives an upper bound, exactly. So the cost is upper bounded by this. So this is a simple data, so it has been analyzed classically, but this is a much simpler maybe analysis, which is kind of automatic, but you have to just observe that this cannot. Okay, so there are a few more examples, but of such analysis, but not too many, I have to say. So this idea appeared like 10, 15 years ago, and somehow there weren't too many cases where it works. So I would like to see, so if you are stuck with some algorithmic problem, maybe give it a try. Can you encode the execution as a matrix, show that some pattern is avoided, and then you get for free an upper bound. It's not so clear when, so you cannot analyze something like quicksort with this, but maybe if your execution has some structural constraint that it may be useful in some. So I will show some more applications of this technique, but somehow it would be nice to find more applications. Okay, so that's kind of the first idea to analyze algorithms. And then I want to say a bit about how to model input structure using combinatorics, but also it will be related to analyzing algorithms. Okay, so going forward, I need just one more definition. So this was mentioned, I think, on Monday in Cyril's talk, permutation patterns. So I just give this one more definition. So if we have a permutation tau, it contains a permutation pi if tau has a subsequence which has the same ordering as pi. So otherwise, it avoids pi. So here is an example. Here is this permutation 3, 2, 4, 5, 1, 7, 8, 9, 6. And this contains the permutation 1, 2, 4, 3, because there is this subsequence 2, 5, 7, 6, which has the same ordering as 1, 2, 4, 3, right? So it doesn't have to be contiguous. It's like subwords in a previous talk. And it also doesn't have to match exactly, just the ordering has to be isomorphic. So both are like this, going up, up, and then a little bit down. Okay, another example, the same permutation contains 1, 2, 3, 4, because it has these 4 elements which are increasing. On the other hand, this permutation avoids 4, 3, 2, 1, because there are no 4 elements which are okay. So it's a natural concept, and we can also view it visually. Here is the permutation, and it contains 2, 3, 1, because there are these 3 points which are in that configuration. And we can define this pattern containment also for point sets in the plane, like a set of points in the plane could avoid or contain some pattern. Okay, and some quick examples. Of course, avoiding 2, 1 means that it's increasing. Avoiding k plus 1k to 1 means that you can decompose the permutation into k increasing subsequences. Avoiding 2, 3, 1 is a famous one. This means that this is stack sortable. So in some sense, this was the original question. So Knut introduced this concept of pattern avoidance, and this was in the early edition of the art of computer programming. This was an exercise that showed that you can sort the permutation by a stack if and only if, in modern language, it avoids 2, 3, 1, right? So you have no ijk such that blah, blah, blah. Okay, and so why it's kind of this, like, how you can in a train yard, can you reverse the trains using a stack? Okay, so this M28 means that I think you should solve it within half an hour or so, but I think nowadays probably in 5 minutes we can. People are much smarter in 2024, so. Yeah, so okay, and here another simple example. If you avoid both 1, 3, 2 and 3, 1, 2, then this is the simple permutation where every entry is either a minimum or a maximum. So you are sort of always, it's called a DEC sequence, or you are always adding a new minimum or a maximum. Okay, but back to this definition. So okay, we have permutations avoiding a pattern, and there is this landmark result, or it was a conjecture first by Stanley and Wilf that, okay, how many permutations are there that avoid the pattern? Only single exponential. So 2 to the order n, where this order n could depend on could include some factor depending on the pattern. So it's much less than n factorial, it's just single exponential in n. And it turns out that this is equivalent with this matrix density question that I mentioned. So Marcus and Tardos proved both in one go. So it was a famous open question for 25 years, and it's one of these rare cases that the proof turned out to be maybe half a page. It's totally elementary proof by induction, or it's a very clever but very simple proof. Okay, so just to summarize these two results, so there are at most single exponential permutations of length n that avoid pi. This is the Stanley-Wilf result. And the density of an n by n matrix that avoids a permutation is at most some constant times n. And these constants both depend on the permutation, and they are kind of related. So if one is polynomial in the other, but it's not fully understood what are these constants. But if the permutation is constant, then these are constant. Okay, so why do I mention all this? So just keep this in mind. There are single exponentially many permutations of length n that avoid the pattern. So this is what combinatorialists were interested in for a long time. But I want to ask an algorithmic question, which I think is also interesting. That okay, take some algorithmic problem which works on a sequential input. Does this problem become easier if the input avoids a pattern? So is it meaningful for algorithms if the input avoids some pattern? So maybe the most natural example, sorting a sequence of n numbers. We know that the complexity is n log n. You have to do n log n comparisons, and you can do it. But what if the input avoids some arbitrary pattern? Maybe we can do it in linear time or with linear number of comparisons. Right, so this is, we can ask this question for other problems also other than sorting, but maybe sorting is a natural case. And it would be nice to have a general purpose algorithm which works for each pattern and not something tailored to each pattern specifically. So why study this? Well, first, this would generalize what is known easy. So we know how to do it, like stack sorting, 2, 3, 1, 2, 1 avoiding, but maybe we can do it for every possible avoided pattern. Also motivation that, okay, there are only single exponential such permutations, then the lower bound is linear, the information theory lower bound, right? Because the logarithm of this is just linear, so maybe we can do it. And in some sense, so this would make this counting result algorithmic. And okay, maybe we can see this as an analogy to graph algorithms, where if you avoid an arbitrary minor, you can do some things efficiently. So maybe if you in your sequence you avoid an arbitrary pattern, you can do things efficiently. So actually we can do this, but it's not obvious. So how should we sort a sequence while taking advantage of an avoided pattern? So the best way we have is to sort by inserting into a binary search tree. So we are doing basically insertion sort. We are inserting into a binary search tree and then reading out in a sorted order. Okay, but what kind of binary search tree? We could use some balanced tree. We saw ABL trees, red-black trees, but these are all logarithmic depths. So log n cost per operation, it just gives n log n for sorting. So we need something adaptive that somehow takes advantage of this avoided pattern. So something maybe similar to, I don't know if people are familiar with this splay tree data structure, which is kind of an adaptive binary search tree. So maybe something like that could be helpful. So what is a splay tree? So a splay tree is a binary search tree where if you search a key or you insert something, then you move it up to the root in a funny way. There are these double rotations. I will not get into the details of this. So let me illustrate on a larger example. So you start with some tree, then you search for something, and then the tree is kind of rearranged in a mysterious way. So this illustration is from an old book by Kurt Melhorn, and he used this German term which somehow didn't catch up or catch on. But yeah, so this is an illustration of a splay tree. You start with, you search for one, and then you also rearrange the tree somehow by rotations. Right, and it's then you search something else, and then you rearrange it. And you could do insertion sort with this. It's called actually splay sort. You are inserting into the splay tree, and then you rearrange the tree in some way. Okay, and maybe this is so this splay tree is a very nice algorithm. Maybe it takes advantage of this avoided pattern. Who knows? Okay, but how can we even analyze this? So it turns out to be not very difficult. So we can use something which is a geometric view of binary search trees. So we can kind of plot in 2D what we do in the binary search tree. So let's say we have this sequence. You could say we are sorting this sequence, but this is how we insert into a binary search tree: 4, 5, 6, 1, 2, 3. And I just plot them, time on the vertical and keys on the horizontal. So I just put 4, 5, 6, 1, 2, 3. Okay, and I can also mark here as dots what happens in the binary search tree. So you do some rotations, you move the pointer around, you update the tree, but whatever happens at a certain time, I can mark with these gray dots. It's the nodes touched by pointer moves and rotations. Okay, so kind of the execution of this sequence is encoded in this matrix. Okay, and luckily there is an exact characterization of which point sets correspond to a correct execution in a binary search tree. And the condition is just this, that there can be no empty rectangle. So there cannot be 2 points which are corners of a rectangle which doesn't have other points inside. So for example, you see these 2 points form a rectangle, but there are also other points in that rectangle. So it's maybe kind of intuitive that if you touch something in a binary search tree at a certain time, then you cannot just jump at a later time to another node miraculously. You have to touch in between, you have to touch some node which is in between. Maybe their common ancestor or that's the intuition. But this is an exact characterization of which matrices correspond to a valid sequence of operations in a binary search tree. Okay, so then we can think of, I mean, this was known before. We can, in this geometric view, give a natural algorithm, which is kind of this greedy sweep line that we go bottom to top, and we add just the minimum points necessary to get rid of all the empty rectangles. Okay, so I cannot get into all the details of this, but this describes an insertion sort execution. So if I'm adding these gray points in this bottom-up fashion, that gives an insertion sort execution, meaning that during the insertion sort, I touched exactly these gray nodes. And now the question is, what is the cost of this insertion sort? So what is the number of dots in this matrix? Okay, and so here we have a nice and simple observation, which is just the following. We have this gadget that consists of 3 points. So remember, the black dots are the input, what we want to sort. And the gray dots are everything else that we do in the tree, the nodes that we touch in the tree. And we have this lemma that if this gadget appears anywhere in the execution, these 3 points in this configuration, then there has to be an input point inside. There has to be a black dot somewhere inside this gadget. Maybe somewhere inside here, or maybe one of these 3 has to be an input point. And again, this is somehow intuitive that if at some time you touch these 2 nodes I and J, at a later time you won't touch something between them unless you are forced to, unless there was some input which forced you to get in that subtree. And this lemma is enough to do the analysis. We call this the input revealing gadget. So if you have this gadget, it reveals an input point. So what do we get from this? Suppose you have 3 copies of this gadget like this. Then each of them reveals an input point. So that means if you have these 9 points, then you reveal these 3 points. Okay, so I can turn it around. If your input avoided these 3 points, then your execution had to avoid these 9 points. Because otherwise, all these little gadgets would reveal an input point and you would have the forbidden pattern, right? So if your input avoids some pattern, then the execution of an algorithm avoids some slightly larger pattern, which is your input pattern blown up with this gadget. Okay, and then again, we can go to the literature and see what is how dense can this matrix be if it avoids this pattern. And it turns out to be slightly superlinear. It's n times some function which depends on this inverse Ackermann function. But more generally, if your input avoids some pattern pi, then the execution of your insertion sort will avoid this pattern pi tensor product with this gadget. So each entry is replaced by this gadget. And so it's I mean, you may notice that this is not a permutation. This is not a permutation pattern, right? If it would be a permutation pattern, we would have gotten a linear bound. But unfortunately, this has these points on the same. So we don't quite get linear bounds, but we get this for now this quasi-linear bound involving this inverse Ackermann function, right? But it's already something. So I said we wanted to be able to sort pattern avoiding permutations in linear time, and we can already sort them in n times something depending on inverse Ackermann function. So it's almost linear. And what's important, we have a general purpose algorithm which has no idea about the avoided pattern, or it's not tailored to the pattern. It just does its a simple thing. And this bound comes out from this analysis that somehow this pattern avoidance leaks through the algorithm, and the execution will also avoid some pattern. Okay, and yeah, so just some remarks. So yes, this pattern avoidance was only used in the analysis. Okay, we can also do, so this was insertion sort via a binary search tree, but we could also do it by selection sort using a heap, a bit similar to this pairing heap data structure, but okay. So the result relied on this extremal function of this this type of pattern, which is some permutation tensor product with this gadget. And of course, this was not widely studied in combinatorics, because why would mathematicians care about this exact pattern, right? But after we had this result, people looked at it more carefully and noticed that, okay, they can tighten the extremal bounds for this type of pattern, and they improved it a little bit, but it's still not linear, and it cannot be linear. So it can be shown that by this argument you don't get all the way to linear. So we need something else. So can we get to actually linear? Yes, but it takes some little bit more ideas. So okay, I will maybe get a bit to that in the end. But okay, this was so far about sorting. I hope it was more or less clear. And before, so I want to do another example also, because I want to show that somehow this phenomenon is more general, not just applying to one problem. So if you lost some of the details of with the data structure or sorting, it's I want to show a fresh example also, something which is a geometric example. So maybe give this example also a chance if you didn't like the previous one. So So okay, so here is a different question. Consider the traveling salesman problem. There are n points in the plane, let's say in the 0, 1 box, and you want to connect, you find the shortest tour. You want to connect them by a tour. And the question is, how long is this tour? So does someone know what's the worst case length of a tour of n points? Square root n, very good. Yes, so the worst case is square root n. And there are many ways to, it's been known for a long time. One way to see it is that you can add this tour, sort of this comb, where all this is 1 over root n, and the length of this tour itself is root n, and then every point is within 1 over root n from joining this tour. So you can kind of collect all the points in. There are other ways to see it, but it's so the asymptotics is root n, and this is tight. You can see it if the points would form a grid of this root n by root n grid, then every point would need at least 1 over root n, even to get to the nearest other point, right? So this is fully understood. What is the length of the TSP tour in the plane? So now I ask maybe an exotic question. What is the length of the TSP tour if your point set avoids some pattern? Okay, is it less? Is it much less? How much less? Okay, so this is maybe in geometric context, it's a bit less natural, but you could ask, okay, it's a restriction of how does the complexity change? And here is a motivating example. If your pattern happens to be 3 to 1, then it means that your points decompose into 2 monotone sequences, and then your cost is only 2 or 2 times square root 2, or in any case a constant, not root n, right? So this shows that there is something going on. So at least for this pattern you get something. But what about arbitrary pattern? Okay, and so here is a very simple argument. We could split this unit box into square root n by square root n grid cells. And notice that not all the grid cells have some point inside. Actually, only about square root n times some constant cells will have any points inside. Why is that? Well, remember this result about matrix density. So this matrix avoids a permutation pattern. So therefore, it cannot have more than linear non-zero entries. And linear in this case means square root n. Right, so only about square root n of the grid cells will be touched. Following from this Marcus-Tardos result on the. And then we can decompose our cost in a very easy way. We can look at all the tour within each cell and then connect those cells into one big tour. So we have this maybe ugly recurrence that, okay, we have this square root n cells. We have to connect them into a tour. So that is this recursion f of that. Right, it's still avoiding the same pattern, so we can use the same function f. And then we have all the little tours inside the cells, and here I'm assuming that each cell has the equal number of. One can use the Jensen's inequality to show that that is the worst case if all the cells have the same number of points, and you get this recurrence. And you work through it, you get something like polylog n. Okay, depending on this constant. So it's the large constant, but it's polylogarithmic. So it's much less than square root n. Okay, so if your point set avoids the pattern, then the tour length is only polylogarithmic. And actually, we can improve this to logarithmic. So log n times this constant, and we can show that that is tight for almost all patterns. So actually, this 3 to 1 was an exception where it was constant. For almost all patterns, it's logarithmic, and and not more than that. Okay, so that's the main thing I wanted to talk about. So I wanted to show this, that okay, some problems get easier if the input avoids some pattern. We have some more examples of that, but I just want to sketch the tool which gets us all the way to linear time sorting and to logarithmic TSP and some other problems, which is this concept of twin width, which is it's a very new or a relatively new concept in computer science. It's applied to permutations. It's a very simple interpretation. It says that if X is avoiding some pattern pi, then its twin width is bounded by the C of pi, which means that X has a C-wide merge sequence. I'll say in a moment what is a merge sequence. I'll have a nice animation. But we can use this merge sequence to construct basically a logarithmic cost TSP tour. And we can use this merge sequence to construct a linear cost binary search tree execution. So this concept of merge sequence gets us a bit further. So let me show what is this merge sequence. So it's a sequence where you start with n points, and in each step you merge. You can think of these points as little rectangles, initially miniature rectangles, and in each step you merge two rectangles into one rectangle. So for example, I merge these two points, in this case, to this rectangle. Now I merged these two. Now I merge these two. They can also overlap. And I can even merge two rectangles. So I can take these two rectangles and merge them into this one rectangle. I replace them by their bounding box. Now I have this. I can merge these two, and so on. And in the end, I end up with one rectangle containing everything. So I have exactly n-1 such merges, and I start with all singletons, and I end up with everything being one rectangle. And that I say that two rectangles see each other if they overlap either horizontally or vertically. So for example, these two rectangles don't see each other. And what I want is to have a merge sequence where each rectangle sees only few other rectangles. That will be the width of this merge sequence. So I say that a merge sequence is D wide if every rectangle sees only at most D other rectangles. So you see, if I have these rectangles and points, this one sees only 3. It sees this one, and this one. This one sees 5. It sees this, and this. Okay, so the theorem is that if your point set or permutation is avoiding some pattern, then you have a merge sequence with constant width. You can merge these points in such a way that there is very little interaction between the rectangles. Each rectangle sees only constantly many other rectangles. Okay, and we can use this merge sequence to construct our solution. Okay, there is still a technicality. This doesn't give us actually a sorting in linear time because it gives an offline binary search tree sequence. So to get an online sequence, it's not obvious how to do it. So there is this famous dynamic optimality conjecture, which says that this play tree is competitive with the optimum. So in that case, play tree would achieve linear time sorting, but actually it can be done to sort in linear time. But the final step was done by my co-author, which is not yet published. So currently there is still we have this we can construct this linear cost binary search tree execution. But for sorting what is published, we still have this alpha n factor. Okay, I will skip more technical details. Let me let me try to summarize the ideas. So the first part of the talk, I talked about using extremal combinatorics to analyze algorithms. And I gave one example, this union find. There are a few other which are similar flavor data structure analysis. But my message would be that, OK, we should find more examples and get more intuition of when can this technique be used to analyze algorithms. And the second message was that pattern avoidance reduces the complexity of algorithmic or geometric problems. And we have some examples from data structures related to sorting. We have examples from geometric problems. I mentioned the TSP, but one can study all kinds of other geometric problems. We also apply this to online problems, this K-server problem, where if I'm not defining it now, but if your input avoids some pattern, then the problem becomes easier. In many cases, we have matching lower bounds, and for some patterns, we have stronger bounds. But it's still a work in progress, and it's a recent work. Somehow, it would be nice to find more examples and to understand more systematically when and why does pattern avoidance make problems easier. So what I presented was mostly based on these three papers, especially this most recent. And here are some other references which I mentioned. And this last paper is joint work with my PhD student, Benjamin, in Berlin, and our collaborator, Michael Oppler, in Prague. So with that, I thank you for your attention.
Not for the talk. I see there are questions.
Hi. Thanks for this interesting talk. I don't know if I will be explaining myself well. Extremal combinatorics can also be used to not to see if, how dense the matrix could be to avoid some pattern, but also how many dots do I need to make sure that I get some pattern, right? And do you have any examples where this kind of reasoning could be used to prove lower bounds instead of analyzing algorithms to show that some problem has such and such complexity at least?
So I don't immediately see how that would work in the data structures or algorithms context. But of course, as you say, there have been many connections between extremal combinatorics and computer science. And I think it has been used in circuit complexity also to prove. But I don't immediately see how you would prove lower bounds. Or I mean, we can talk offline. I'm curious to.
No, I was curious to know if there are examples where you can use these kind of ideas for the opposite, not to analyze an algorithm, but to prove some kind of lower bound.
Yeah, so but somehow here it's the argument is that, okay, you cannot have too many without creating the yes.
Thank you.
So you are bypassing Sebastian. So Conrado was asking about lower bounds. You presented upper bounds, but in some cases it was you were saying that in fact it was equivalent. And for example, perhaps on slides 8 or something like this, you had a full list of different types of funny asymptotics with some 2 to the polylog or Ackermann function. And in those cases, is it the case that it's just a big O and in fact it could be smaller? Or do you know that it will be exactly this? And if yes, in which way you can reach that it is exactly of this order with those methods, which seems to me more to give some bounds?
So I can say that. Okay. Yes. So the situation is that for these concrete small examples which have been studied, usually there are tight bounds up to the constant. So for example, for this pattern or something like that, it's usually tight results, and especially combinatorialists are always interested in finding the extremal example. Like it's even more interesting than the upper bound. What is the configuration that realizes it? But for this more general case where we say for every permutation, of course, there is a huge constant hidden here, which depends on the pattern, and there we cannot really hope to be to have tight result. Yeah, so I have it. Yes, sorry. So it's a very big question. Okay, sorry for. Yes, so it's a very big question. What are these constants C pi and S pi for each pattern in particular? And we know that it cannot be more than single exponential in this pi. So it's like 2 to the pi, but sometimes it is polynomial. And it would be very nice from combinatorics point of view to understand when are these constants polynomial in the pattern length, when are they exponential, but it's out of reach at the moment. It's something which combinatorialists are interested in. And that has to do with how tight these bounds are up down to the constant. Okay.
Other questions?
Sorry, this might be a very dumb question, but I don't quite understand the definition of see each other. I mean, you said it's overlap, but then
Yes, so I
slides.
meant, yes, so this last part, this merge sequence is what I meant by two rectangles seeing each other, means that they overlap in the projection to X or the projection to Y. So for example, these two black rectangles see each other because they overlap on the vertical, but these two in the corner don't see each other because they are disjoint in their X projection and Y projection.
So if it's only boundary overlap, is that still overlap?
So this is still overlap. Yes. So if they overlap when you project them down, and I mean I didn't get to that, but so basically if you have low overlap, it helps when you are constructing, let's say, a TSP solution. You can make the solution cheaper if there is little overlap. Yes.
And also, like the pattern avoidance you consider seem to be a higher dimensional generalization of the one-dimensional pattern avoidance problem. I mean, for one dimension, people consider limit shapes of those things. Like, have you considered limit shapes of these objects?
Yes, so that's a direction which I'm not so familiar with. I know that probabilists have studied like what is the limit shape of pattern avoiding permutation, like sort of if you overimpose every pi avoiding permutation, how does it look like? And I'm not very familiar with those results, but it's kind of, they look very sparse when you look at the limiting shape. Like some parts are much more probable that you have a point there than in other parts. And somehow what I want to say that this fact that there is a short traveling salesman tour, we wanted to capture that sparsity in a different way. That this point set is somehow they are sort of clustered in. But yes, I'm not very familiar with this direction of these permutation limits, and there is a lot of work in that direction.
Yeah, I feel like the problem you consider seem to be like extending that direction in something. Thank you. Oh, wow, this is like a linear transition.
Thanks, László, for your talk. I have a question. So now we know that if your permutations avoid some patterns, we can very quickly sort them.
Yes.
But do you know how this results projects to the words? If your input contains some repetitions and also avoid some patterns, is it possible to adapt your result?
Yeah, so I focused on permutations. Like I assume that these input elements are distinct, but it's usually not really an issue if you have repetitions. And there are different ways to see that, but So one, you can extend pattern avoidance also to sequences which may have duplicates, but also you can do a standard perturbation. Like if you have equal elements, you can add an epsilon to. So if you look at it visually, like let's say this point set also contained points which were aligned on some vertical line. You could slightly tilt the entire thing, which means like you add some epsilon, some 2 epsilon, some 3 epsilon to the elements. And then if your original point set avoided some pattern, then this tilted point set also avoids some slightly larger pattern.
Yeah, but for example, if your pattern is also a word, so if you take a word that avoid pattern 1-1, it will be a permutation, and so you need to n again.
Yes, yeah. So I was referring if your pattern that is always a permutation.
Okay.
But if your pattern itself is
it's a word,
it gets more tricky. I think that was not so studied, but it's also like okay, if you avoid 1-1, that just means that you don't have duplicate.
yeah, maybe it's only a difficult case, but okay, interesting.
Yes. So I think that somehow it becomes different in that. Yes.
Thanks a lot.
Other questions? I have a detailed question about what I remember from twin width. What would be the merge sequences? These are not easy to compute. For twin width is even, I think the complexity of computing them is unknown, even if you know the graph has low twin width. Is that a problem here?
No, so that is true in graphs, but this is sort of so twin width has been extended to graphs, and but in point sets and permutations, it's very nicely behaved, and you can compute basically this optimal merge sequence in n log n time. So what does it mean? You are constructing a binary search tree execution, which will take linear time, but you are taking n log n time to find it. So that's why it doesn't immediately give an efficient sorting, but it's not more than n log n. It's basically it's a greedy algorithm. Basically, you greedily merge nearby rectangles, and it just happens to be good.
Yeah, it helps that things are already ordered. Yeah. Other questions? And thanks to László.